Jai Hind everyone. My name is Dr. Dibya Bharti. Today we are going to discuss topic source transformation. Subject name is network analysis and synthesis with subject code KC 303. So earlier we were discussing mesh analysis, nodal analysis. Okay, so we had discussed this in DC network. These topics will be discussed in AC circuit also. But today we will first see source transformation. This source transformation is useful while we solve the numerical problems. Okay, suppose any voltage source is there in the network and resistor is there in the series with the voltage source, or current source is there and in parallel with that current source, if any resistor is connected, then that current source can be transformed into the voltage source. So this source transformation makes network easier for the analysis. How, that we will discuss today. So source transformation is a process in which the circuit can be simplified or modified. Okay, in this process, we transform voltage source into current source, or current source can be transformed into voltage source. So basically this process simplifies the network. Okay, so there are many ways to solve the circuit to make it simple. So source transformation is one of them, and this process of simplifying a circuit solution, especially with mixed sources. Okay, when in a network there is voltage source and current source as well. Okay, both type of sources are present, then this source transformation is useful. So the transformation can be derived from this source transformation has been derived from the uniqueness theorem. Okay, so this uniqueness theorem states that basically this uniqueness theorem is the electromagnetism uniqueness theorem, and this states that providing boundary condition for Maxwell's equation uniquely fixes a solution for these equations. Okay, so this is the theorem of uniqueness, or you can say electromagnetism uniqueness theorem. It states that for the provided boundary conditions, Maxwell's equations uniquely fixes a solution for all these equations. Okay, so based on this theorem, the source transformation has been derived. So performing a source transformation consists of using Ohm's law to take an existing voltage source in series with a resistance and replacing it with a current source in parallel with the same resistance, okay, or the vice versa. So by using the Ohm's law, we transform voltage source in series with resistor into the current source in parallel with the same resistor, or a current source with parallel resistance can be transformed into voltage source in series with the same resistor. Okay, this we perform by the Ohm's law. The transformed sources are considered identical, okay, and can be substituted for one another in a circuit. Okay, so we can substitute current source in place of voltage source, and voltage source can be replaced by a current source. So source transformations are not limited to resistive circuit only. Okay, so they can be performed on a circuit involving capacitors and inductors as well. So by expressing circuit elements as impedance and source in the frequency domain. Okay, so the source transformation is applicable in the network where capacitors and inductors are present also. Okay, so in that case, if resistance and inductor is there, or if resistance and capacitor is there, then we refer impedance, okay, not resistance only. So we take total impedance in series with voltage source or total impedance in parallel with current source, and the sources will be in the frequency domain. So see, if any circuit is having the voltage source in series, it can be converted into current source with parallel that of resistor. Okay, so this process can be reciprocated also. So if any voltage source is there and a resistor is there in the series, then that can be converted into current source with the resistance in parallel. Okay, the same resistance will be connected in the parallel, as we can see here. So see here, this is the voltage source Vi and resistor R is in series. So this can be transformed into this network. Okay, so in place of voltage source, we will be having the current source, and the same resistor will be connected in the parallel. So the value of this current source Is, this we can write this, suppose Vi is the voltage source. Okay, so by Ohm's law we can write this as Is will be Vi by R. So the magnitude of this current source is Vi by R, and we will connect the same resistor R in parallel. So these are equivalent. Okay, and this process can be reciprocated. Okay, so suppose we are having this type of network, this type of that Is is the current source and resistor R is in parallel. Okay, so this can be transformed into the voltage source as well. So in that case, we will write Vi. Okay, V is I into R. So we will multiply this Is into R. Okay, so value of this voltage source is Is into R, and value of this current source Is is Vi by R. Both network are equivalent to each other. So now, if see here, two voltage sources V1 and V2 are connected in series. Okay, so these two sources can be represented by an equivalent single source. Okay, so here V1 and V2 are connected in series, and there is an additional of two sources in one of them, and it is connected in parallel. Then in both voltage source would be same. Okay, so here V1 and V2 are two voltage sources, those are connected in series. So equivalent to this is the V equal to V1 plus V2. Okay, so now we can transform this. If resistor R or any other resistor is there in the series with this source. Okay, similarly here, two current sources I1 and I2 are connected in parallel. Okay, then there is addition of to both of the current sources. If both of the current sources are connected in series, then the current is the same in both of the sources. Okay, so see here, I1 and I2 are the two current sources. So equivalent to this will be I1 plus I2. Okay, so this is equivalent I1 plus I2. Here, if voltage source is connected with resistance in parallel, then the resistance can be neglected. Okay, if current source is connected with series resistance, then the resistance can be neglected. Okay, so here voltage source is connected with a resistance R in parallel. So here this resistance can be neglected. If current source I is there and the resistance is in series, so here we can neglect the resistances. Okay, so this is to remember that if voltage source is connected in parallel with the resistance, then that can be neglected, and if current source is connected with resistance in series, then the resistance can be neglected. So now here we will consider few examples. So here consider the two circuits, those are given. In particular, here we can these are the RS and RL. Okay, so here look at the current and voltages of RL. Okay, in both the circuit. Here RS and RL are in series. Here RP and RL are in parallel. So here in this case, if we calculate the current and the voltage across this RL, okay, so IRL, that means the current that is flowing through this resistor RL, we can find out this as Vs divided by Rs plus RL. So that will be 5 Okay, so in first case, IRL, in first circuit, IRL, okay. So in first circuit, the current IRL, okay, will be 5 divided by 2 plus 1. Okay, so now this value is in milliampere. So 5 divided by 3, 5 by 3 milliampere. Okay, so now what will be the voltage? VRL. VRL, we can write this as 1 into 5 by 3. Okay, so this means it is 1.67 volt. Okay, so IRL is 1.67 milliampere, VRL is 1.67, and power is 2.78 megawatt. Power, we can calculate this PRL will be IRL square. So 5 by 3 whole square into 1. Okay, because 1 kilo ohm resistor is there. Okay, so it will be in the milliwatt. So 2.78. This is 2.78 milliwatt. Okay, so now in second case, see what we had done. This voltage source Vs has now been replaced with this current source. Okay, and what will be the value of this current source? Value of this current source will be 5 volt divided by 2 kilo ohm. Okay, so 5 by 2. So 5 by 2, that is 2.5 milliampere. Okay, so this has been replaced, and this RS is now connected with the parallel to this current source. So now we have connected this 2 kilo ohm in parallel with this current source. Okay, so now again we are calculating the values. Okay, so IRL, what will be the value of the IRL in this case? The 2.5 milliampere current source is now being divided. So we had applied here the current division rule. So it will be 2.5 into 2 divided by 2 plus 1. Okay, so now 5 by 3 again. So it is 1.67 milliampere. Okay, VRL, IRL into 1. So it is 1.67 volt and power. Okay, so from the point of view of the resistor RL, the series combination of the voltage source and resistor RS gives the exact same result as the parallel combination of current source and the resistor RP. Okay, so this is the conclusion. So now the series combinations seems to behave identically to the parallel combination that we had discussed. So this suggests that we may, in the right circumstances, replace one configuration for the other. So making this switch to known as this type of change or this type of transformation in the network is known as the source transformation. Okay, so now this is the conclusion about this part, that IS is Vs by Rs, Rp is Rs, and here Is can be replaced with this Vs, and the value of this Vs will be Is into Rp. Okay, but the value of the resistance will be same in both the cases. Only the position of the resistance can be changed. Okay, so now these are source transformations are perfectly viable substitutions. So from the point of view of whatever circuitry is attached to the two terminals, the result will be exactly the same for the two source configurations. Okay, that we had solved and that we had concluded from the numerical problem also. So if you are trying to calculate something about the two components VSRS or IPRP, you cannot transform them. So in transforming them, okay, you lose the ability to calculate the specific property. So this is an example of bigger more important idea that is known as the Thevenin equivalent of the circuit. Okay, so we will see this Thevenin equivalent of the network in our next lectures. Okay, so and that is used to in the amplifiers also. We will discuss that Thevenin equivalent circuit. Okay, so here this is the example. Here see Vs R1, R1, R2, R3 and R4. These three resistances are in parallel and R1 is in series with the voltage source. So here question is find IR4, that means current through this resistor R4. Okay, so now using source transformation we can easily find out the solution, because here parallel number of networks, parallel connected elements are there. Okay, so if we convert this voltage source into the current source, then by current division rule we can easily calculate the current. So now here the voltage source Vs can be transformed into the current source, and the value of that current source will be 50 divided by 25. Okay, so Is is so the value of the current source Is is 50 by 25. Okay, so this is 50 by 25, that is 2 ampere. Okay, so now the 2 ampere current source is connected and the same resistors 25 is now connected in parallel. So now the current division rules, according to this we can calculate the IR4. Okay, so this will be Is, since we are calculating current in this resistor, so reciprocal of this will be multiplied with this Is, and reciprocal of rest all the resistors, and we will calculate the sum. Okay, and we will divide. So now by the current divider rule, so this has been calculated with very ease. So 1 by R4 is 100, 1 by 25 plus 1 by 50 plus 1 by 200 plus 1 by 100. Okay, we had calculated the reciprocal of all the resistance, summation of this. Okay, we had calculated this current IR4. Okay, so it is very easy to calculate the current in this case by the source transformation. Okay, so now this is the second example. Here see, here mixed type of sources are there. Okay, one voltage source is there and one current source is there. Okay, so in this case also it will be easy if we apply the source transformation. Okay, see here also in the question it has been said that find current IR2. Okay, that means current in this resistor R2. Okay, so now better we will convert the voltage source into the current source. So that means if we transform this voltage source into the current source, value of this current source will be Is. Okay, so it will be 20 volt divided by 5 kilo ohm. Okay, that means 4 milliampere. Okay, so now 4 milliampere current source is connected. This 5 kilo ohm resistor and 7.5 kilo ohm resistors are now in parallel. This is the 2 milliampere current source. Okay, so now what we can see here, two current sources are there and we can calculate the equivalent of this also. Okay, so direction of both the current sources are in the same way. So we will add this. So 4 milliampere plus 2 milliampere. This is the equivalent, 6 milliampere. And now we will apply the current division rule. Okay, so by using the current division rule, now 6 milliampere, here we will calculate the current through the 7.5 kilo ohm. So 6 into 6 into 5, 6 into 5 divided by 5 plus 7.5. So it will be 30 divided by 12.5. So I think it will be 2.4 milliampere. Okay. So here, see, this is also the case, very same case, that one voltage source and one current source is there. Okay. In previous example, we had seen that the source transformation is working very nicely. Okay. So we will use the same method. Okay. Here first. So now what we can do here, the same voltage source 40 volt and the current resistor is 1 kilo ohm. So that has been transformed here. So equivalent current source is 40 milliampere and the resistor 1 kilo ohm is in parallel now. So this is 1 kilo ohm resistor, and now 15 milliampere current source was present earlier also. So now if we calculate the current IR1, okay, so now we will add this 40 milliampere plus 15 milliampere. So total 55 milliampere current source is there, and now two resistances of equal amount are in parallel. So that means 55 by 2, that is 27 by 27.5 milliampere current. It seems nice, but it is wrong. It is now in earlier example also there was same case. We had applied the source transformation, but in this case it is wrong, because you cannot transform the component for which you are trying to find the voltage or current. Okay, so this point is to be remembered, since we were required to find out the current through this resistor. Okay, so we cannot transform, we cannot make such type of transformation in which we are trying to find the voltage or current. Okay, so to see that it is wrong, okay, because we had transformed the resistance in which we were trying to find out the current. Okay, so again we will do the source transformation, but we will not transform resistor R1, okay, because we are required to find out the current in this case, okay, with the resistance R1. So now what is the option? Option is to transform this 15 milliampere current source into the voltage source. Okay, so this 15 milliampere current source and in parallel resistor R2 is there. So 15 into 1, 15 milliampere into 1 kilo ohm, so it will be 15 volt voltage source. 1 kilo ohm resistor is now in parallel. So now we will calculate the current IR1. So now what is the, see here, 40 minus 15, okay, so 40 minus 15 divided by 1 plus 1, that is the 12.5 milliampere is the correct answer. Okay, so this point is to remember. So now this is the another example. This is the some circuit. Okay, VS1, VS2, two voltage sources is there, two voltage sources are there in the network, and current source IS is there. So question is to find the VR5. Okay, that means voltage across this resistor R5. Okay, so now what we can do now here, since VS and resistor R1 is in series, so we have transformed this into the current source. This voltage source 60 volt and R2, so this has been transformed again. So this is the 12 ampere and the resistor 5 ohm. So now IS 36 ampere and R3 6 ohm, and this is the network. Okay, so now we need to put the attention onto the polarity. Okay, so here this is the positive terminal of the source, so this current source will also give the current in the network in this direction. So here this is the positive terminal, so this source is giving the current in this direction. So that means equivalent current source also should give the current in the same direction. So that's why direction of this current source is like this. Okay. So now we had simplified this. See here, this 36 plus 6, and now we will minus this, okay, because 36 and 6 ampere. So now 42 minus 12, 30 ampere. So this is the simplified circuit now, and we had calculated the voltage. So this is the another example in the AC circuit. So this is for the practice purpose. All of you can try this. Solution is also provided. So this was all about the today's discussion about the source transformation. Okay. So in next lecture we will continue our discussion. Solution of this last example is also provided, but you can try it your own. So thank you.